Okay, first we need to talk. Last time, um, you, it, um, we worked on this question, right? So, top of the page, it reads no calculus allowed. I thought it reads no calculator. So, for the first tangent line, if you remember, I said that in order to find the slope of the line, you can cheat and use the derivative of the function. That was not allowed. So I'm just going to redo it. You have to revisit this question. It's just going to take 5 minutes. So just to recap, there is this curve and there is this point, -1 and 0, and we are looking for only the slopes of two lines that pass through this point, -1 and 0. And if you remember, we said that let's consider the class of all the straight lines that they pass through this point, -1 and 0, and then we said that there are going to be intersections of 3 of them generally, but at 2 points, in 2 cases, we will have only 2 intersections. We did some math and we found the x-coordinates of these intersections, right? So the first one was -1 as ever, always -1 is fixed. The second one, I'm just going to call this point 2. So the first one is 1, right? 1 is always fixed. Its x-coordinate is -1. 2, its x-coordinate is 1 minus square root 1 plus 4m whole thing divided by 2. And then there is a second one. I'm just going to call it 3. Its x-coordinate is given by 1 plus square root 1 plus 4 times m whole thing divided by 2, right? So we have 3 intersections. X-coordinate is given by -1, 1 minus square root something divided by 2, and the other one is 1 plus. Does it make sense? 3 is the furthest point, right? Because it has 1 plus some positive. It just gets you further and further, right? Okay, so this is at a straight line. When it goes down, so general case, there are 3 intersections. See, the first one is always this -1. The second one is here, and then the third one. It's just like a flip-flop. Let's bring it down. Still, we have 3 points, but point 2 and point 3 are getting closer and closer. Does it make sense? I'm just bringing it down. So point 2, point 3 closer, but point 1 is always fixed. Until point 2 and point 3, they actually meet, right? This is the point that point 2 and point 3, they are just located at one point. That gives you the first tangent line. So if you want to find this one, you have to solve this equation because we said point 2 and point 3, actually they are just one point, right? So x-coordinate for point 2 is equal to the x-coordinate of the point for point 3. That means 1 minus square root this guy divided by 2 is equal to 1 plus square root this guy divided by 2, right? You solve this, you find m, and this m is given by -1 divided by 4. Does it make sense? Right? Everybody clear?
Can you zoom in a little bit?
Zoom. Good? So, point 2 and point 3, they are just referring to one single point. That gives you the first tangent line. How about the other tangent line? So, again, back to the class of straight lines. Let's just pull it up. Still we have, here that's the tangent line. We have 2 intersections. If I lift it, they're going to be 3. So it's still 3, but the point is that point 2 now moving towards point 1. See, they're just getting closer and closer and closer. Point 1 is always fixed. It's always -1. It's not going to move. But point 2 is kind of tending, right? It's just getting closer to point 1 until they meet, which is at this point, right? So point 1 and point 2 at this one extreme point, they are actually pointing to one single point. They are just referring to one single point. They are basically one point. That point is -1 and 0. So here I'm not concerned with point 3. I'm just saying that the second tangent line is a case when point 1 and point 3, they are just one single point. And that single point is given by -1 and 0. So you have to solve a second equation to find that m, which is -1 is equal to 1 minus square root this guy divided by 2. This gives you the second tangent line. This one was the first. Okay, so the first one, point 2 and point 3, and then the second one, point 1 and point 2, right? So this time we didn't cheat, we didn't use calculus. Clear? Any questions? Good. So hope everybody has this workbook now. It's 2014 edition, and I checked with the prof. 2013 edition is slightly different from 2014, so you have to buy this one. Patrick emailed me yesterday and said that he was not able to pick up the book. You can go to the math department, Jeffrey Hall, whenever you want. Go to the main office and get this book. $10 again. You're not gonna pay more, just $10. So, okay. So if you guys have checked the book, there are 3 chapters. And chapter 1 is called partial derivatives. And then I just wrote down the week, the weeks or the time that we are supposed to finish these sections: lines and curves, planes in 3D space. So the first and second week, we're going to be working on the first 3 sections. And then we have 3, 4, 5, 6. And then you may think that this is the end, but it's not. We have chapter 2 here. Chapter 2. Yeah, chapter 2 here, week 7, 8, and 9. And again, you may think that, oh, this is the end. Still not. So we have chapter 3. Chapter 3 series. Here we go. Week 10, 11, 12, final, and you're done. So, good. Okay, we are familiar with concepts like lines. One of the objectives in this course is that to formulate these abstract concepts. So let's consider a straight line like this one, right? In order to formulate this object, this abstract concept, or to formulate it, you actually need 2 pieces of information. One is at least you need to know at least one point that this straight line passes through. At least one point. And then, second piece, you need a vector that shows the direction of this line, right? With these 2, you can characterize this line 100%. How? Using this equation. V is equal to V naught or V0 plus T times U. And I'll tell you what these parameters are. U is any random point on this line, any random point. So depending on the space that you guys are dealing with, 2-dimensional, 3-dimensional, 4-dimensional, n-dimensional, it gives you the size of that V. V is a vector of size n times 1, n being that space. If it's a 2-dimensional space, V belongs to R. So depending on the space, V belongs to R 2 times 1. So that 2 times 1 gives you the size of that vector, right? V naught or V0 is that single point that this straight line goes through. You only need one single point. And again, the size is exactly the same. it belongs to R, which is the real numbers, right? Any real number. And then 2 times 1, it gives you the size. What is T? T is a real number, just one scalar real number, anything from minus infinity to plus infinity. And then U is that vector of direction. So again, size is the same. It belongs to R to the 2 by 1. So V naught and U, they all belong to R, which is the real domain, right? Real numbers, but a vector. That's why it has a size 2 by 1. But T, just a real number. So this way we parameterize this line. So there are other representations for this equation. So as I said, V can be, x, y, z if it's a three-dimensional space. If it's only two-dimensional space, you're gonna only need this x and y, right? So this is for two-dimensional case, and the whole thing is for three-dimensional case. And V naught is just x0, y0, z0, just one single point that this line passes through, and then U is the vector, right? A, B, C, T is just a scalar. A question for you. Do you think if this equation is unique? Do you think if for one line there is only one equation? The way that I asked it, the answer is obvious. Right? You can say no, it's not. So because one can say that, okay, I'm going to pick this point and then this vector, right? Someone else can say, oh no, I'm going to pick this point. Someone else can, I'm just going to pick this point. The length is infinite, right? It's just a long, long line. So this representation is not unique, but the line is unique. So if you solve a question related to lines, and then you come up with different equation, it's okay. As long as the steps make sense, it's okay. But it's not necessarily you will have all the same answers. So to reinforce these topics, let's do a couple of examples. Example 1, find the parametric equation for the line that passes through this point 2, 1, 0 in the direction of vector -1, 1, 2. It's obvious, right? So 2, 1, 0 is which parameter? Okay, we need two parameters, right? We need V naught or V0, and we need U. So this point gives us which one? V naught, perfect. And then that vector -1, 2, 1, and 2 gives us U, wonderful. So we are done. So we have V is equal to 2, 1, 0 plus T times -1, 1, 2, right? Okay, again, it's not a unique representation, right? Someone can just say, instead of this direction, this vector, I want to pick this one divided by 2. It's still okay. Someone can say, I want to just divide it by 20. It's still okay. Because what you care is the direction, right? When you are, let's say you're looking for the direction to Toronto, it doesn't matter how long my arm is, right? It's just pointing to Toronto. Hopefully it's this way. So it doesn't matter how long this vector is. You can divide it by 2, you can divide it by 20, you can multiply it by 100 million. It still doesn't matter. The only thing that matters is the direction. Even you can multiply it by for lines, it's okay. You can multiply it by a negative number, which is kind of counterintuitive because the direction here matters, right? If it's Toronto, then this is Montreal. But for lines, they don't have any direction. So you can say the direction is -1, 1, 2, or actually you can say the direction is 1, -1, -2. It's exactly the other way, but it's still okay. For lines, it doesn't matter. Okay? Perfect. And then make a sketch of the line and illustrate the parameterization. Hope I got the pronunciation right. So if you want to sketch a line, you only need 2 points. 2 points. If you want to plot it, you only need 2 points. So let's do it. The first point is obvious. It's given, right? It's given 2, 1, 0. I'm just going to call this one point A. And then point B. okay, so I'm gonna just stick to the original equation that I wrote. So V is 210 plus T minus 1, 1, 2, right? I'm just gonna pick one T, which is not 0, anything. I'm just gonna say T is 1, because I need only one single point, right? So for T1, okay, so what's the coordinates of B if T is 1? So I'm just gonna use this equation, plug in T is equal to 1, and read V for me. What's the first one? 2 plus, it's 1. The second one, 2. Third one, 2. Wonderful. So I just need, so this is X, this is Y, this is Z, right? So the first point is 2, 1, 0. So this is 2, and this is 1 and 0, right? So this is point A. And what's point B? 1, 2, 2. So this is 1, this is 2, and this one has elevation 2. So this is something like point B. And then you just connect these 2 points. This gives you the line. Clear? So if you want to plot a line, you only need 2 points working with that. So start with the equation. So for that equation, again, to recap, you need 1 point, 1 vector, and then write down the equation. You already have 1 point, you need another point. Find that point, and then locate those 2 points, and then you're done. Just connect 2 points, and you're done. Clear? Wrong?
Is V just another point then?
V is any point on this line,
Okay.
because t varies from minus infinity to infinity. V can be any point. Someone can say, okay, I'm not happy with t is equal to 1. You can pick t minus 1 or t2 or t10. But the problem with t10 is that it's just going to give you some big numbers that, let's say, if t is 10, and then you have 8 here, and then 11 here, and then 20 here, right? It's kind of hard to plot it here. So, but pick t, which is any number, not 0. Because 0 just gives you the first point that you already know. You need a separate point. You need another point, right? Okay, so interpret t as time and calculate velocity and speed. I'm pretty sure you guys know this equation and just these terms, velocity and speed. So I'm just gonna rewrite their definitions. So velocity is derivative of x with respect to t, derivative of y with respect to t, and derivative of z with respect to t, right? This is the velocity. So, and then speed is the norm of velocity, which is square root dx to dt squared plus dy to dt squared plus dz to dt squared. Right? Okay. So let's just start with velocity. Using that equation for the line. So remember that this v is x, y, and z, right? And then, so using this equation, I know that x is 2 plus, or actually minus t, right? And y is 1 plus t. Z is 0 plus 2t, right? I'm just going to write them down again. So x is 2 minus t, y is 1 plus t, z is just 2t, right? I'm just rewriting the equations that we drew earlier. So Next step is to use this definition for velocity and then find the derivatives with respect to t. So x is 2 minus t. What's dx to dt? Negative 1. What's dy to dt? What's dz to dt? Then there we go. It's minus 1. This is the velocity. And then what's the speed? The speed is negative 1 squared plus 1 squared plus 2 squared, which gives us square root 6. Right? Clear? Questions? Nice. Okay, example 2. Find the parametric equation for the line that passes through points A and B. Okay, I'm not going to solve it completely. I'm just going to give you a hint. As I said, to use that equation, you need 1 point, 1 vector, right? But here you are given only 2 points. So for the point 1, you can pick either A or B. You can say it's 1, 2, 3 or 1, 4, 4. Doesn't matter, right? You need U. U can be given by A minus B. That's the whole thing, right? So use that equation. Use that equation. V is equal to V naught plus TU. For T naught, for V naught, you can pick either A or B, doesn't matter. For U, use A minus B or B minus A. Clear? So why? The reason is that this is just a line, right? This is A and this is B. So I'm just going to pick this one as V naught, and then I need the direction. Direction is a vector that connects A to B, or actually you can say connects B to A, doesn't matter, right? So this vector is given by B minus A, or actually this direction that I said, it is actually B minus A. Or someone can say, oh, I want to pick this vector, the other, from B to A. So this one is given by A minus B. It's up to you, your call, either A minus B or B minus A, right? Everybody clear? Then you use that equation and you will get the answer which is given here. Okay. Everybody clear here? Example 1.3. Please, when you go home, redo these examples. Don't just take it for granted that I have the solution and then everything is okay. Please redo them. So find the parametric equation in R2 for the line y is 2 times x plus 3. So the answer is given, right? The answer is given. So this way, you're just saying that x is that parameter that is just any random parameter like t. And then when x is t, right? When x is t, then y is 2 times t plus 3. And we can just rewrite it as x and y equal to some t times, because here it is t times 1, right? So I have 1, I have 2, 1 here, 2 here, plus I have 0 here and 3 here, right? This is the easiest way. Someone can say, yep.
What is the R squared mean, R2?
Okay, first R means that x is a real number, y is a real number, and R2 means that 2 gives you the size of that vector. X and y together they are a vector, right? The size of that vector is 2 times 1. So sometimes they say it is it's two-dimensional space, right? That's the size of the vector, 2 times 1. So if it was R3, you would expect x and y and z. If it's R2, then it's only x and y, right? Okay, so this is the easiest way, right? But someone may say that why should I say x is t? Just I like to say x is actually t plus 10. It's okay. And then, so we are done with the first, the solution, right? This is just another thing. This is just a different answer. One can say, oh, I want to say x is t plus 10. And then that being the case, y is given by 2 times that thing that you said, t plus 10 plus 3. And then you have another parameterization for this thing. So it's not unique. It is not unique. The first one is just the easiest one, right? You're just saying x is t, and then you have the equation for y, which is 2 times x plus 3, and then you're done, right? So this is solution 1, which is pretty standard. Solution 2, one might say, oh, I'm not happy with x is equal to t. I just want to say x is t plus 10. It's okay. And then you have another solution for y, right? So it's your call. You can pick either the first one or the second one, or any other strange form. It's okay. As I said, that these representations, they are not unique. So this is okay, and this is okay too. But go for the first one. Clear? And then for this one, if I continue this one, I'll get x and y is equal to t 1 and 2 here, and then 10 and 3 here. Right? Yes?
Why did you make x equal to 2, sorry?
Well, as I said, why did I do that?
You just do it.
Okay, let's say, you remember this equation that we had here? So this general equation, it only has one nice parameter t. And if I change this parameter, it gives me the whole range for all the possible values of the points over the line, right? On the line. So I'm just going to stick to the same form, and then basically this question is asking to change this. This is a line, right? Y is equal to 2 times x plus 3. This is another line. So the intention of this question is to use or to turn it into that previous form that we had, right? It's just a form thing.
How did you come up with that direction?
So this y is equal to 2 times x plus 3, right? So as I said, I want to use the previous form, the form that we just introduced at the beginning of the lecture, right? So I said that let's say x is t, and then using this equation, I can express y in terms of t, right? So x is t times 1, right? And then y is t times 2. Okay, and then go back and check this equation. So whatever is multiplied by t is that direction, right? So here I have t times 1 and 2. Here I have t times u, right? So this u is actually this 1 and 2, right? Clear? Good. Example 1.4. Show that the lines L1 and L2 are askew, which means they do not intersect and they are not parallel. So have a second. Yeah. So in the three-dimensional space, if you consider two straight lines, 3 scenarios are possible. One, they are parallel, right? They are just parallel lines. This is scenario 1. And when does it happen? When the direction of this vector is something times the direction of the other. So I'm just going to write it down for you guys. So 3 cases are possible. Case 1, parallel lines, when u1 is the direction of line 1. If some number, I'm using alpha. Alpha is just some number. Can be negative, can be positive, it's just a real number. Times the direction of the other one. Right? So 2 lines. Let's say the direction of this vector, this line is 1, 1, 1. The direction of this one is 2, 2, 2. Right? So the direction of this one is 2 times this one. Then they are parallel. Right? Second case is when they intersect. This case is when you can find one point such that, so just I want to recap, use the equation that we just learned, right? So any point on line 1 is V is V naught plus TU. And then for the second line, I have a similar equation. For the first one, because I'm referring to the first line, I'm just going to add 1 and 1 and 1 here, and then actually another 1 here, right? Because I'm talking about line 1. For the second one, I'm just going to add these 2's here, 2, 2, 2, 2, right? Two lines intersect. If you can find a T1 and T2 such that this equation has a unique answer. Might seem abstract. We're going to do it now. Just write it down, and then we're going to work this example out. So, and then this, okay, if it's not parallel, if they don't intersect, then they are skew. Otherwise. Okay? So, in order to check if two lines are skew, then you have to show that they are not parallel and they do not intersect. Right? There are only 3 cases possible. So, let's do it. Okay. First, are they parallel? What's the direction vector for line 1? What is U1 here? Answer, guys. What's the direction for line 1? No, line 1. It's what? -1, 1, and 2. And what's the direction for line 2? 1, 2, -1. How did I get it? So, again, back to the equation, right? Look for T. If you have T, then you have the direction. The other term is that single point that this line passes through, right? So, these lines are parallel if I can find something like alpha such that -1, 1, and 2 is equal to alpha times 1, 2, and -1. So, this one can be written as alpha times 1, alpha times 2, and alpha times -1. And here I have still -1, 1, 2. Okay. 3 equations and 1 variable, 1 parameter that I need to find its value. The problem is that it's impossible to solve it. Why? Look for, the first one is alpha times 1 is -1, right? So the first one means that alpha is -1. The second one, 2 times alpha is 1. That means alpha is 1 over 2. And the third one actually means that alpha is -2. So that means such alpha does not exist. So these 2 lines are not parallel. Clear? So I started with this assumption saying that, oh, they are parallel. Then such alpha must exist. And I went through with this assumption that, oh, such alpha exists. And then in order to find that alpha, I have to solve this equation that U1 is alpha times U2. And actually it turned out that it doesn't exist. Then my assumption is wrong. Right? So they are not parallel. Do they intersect? Let's see. So 1/3 is done, right? Do they intersect? If they do, then I should be able to find a proper value for T1 such that this left term is equal to the right term, right? Okay, how did I get it? The left side is basically copied and pasted from the equation of line 1. And the right side is just copied and pasted from the equation for line 2. What I'm saying by this equation, I'm just saying that there is a single point that belongs to line 1 and belongs to line 2, right? If 2 lines intersect, there is one single point that belongs to line 1 and belongs to line 2. Therefore, I can use, for this single point, I can use both equations. Both equations hold, right? Because this point belongs to both of them. So I can, this point belongs to line 1, then I can use this equation. This point also belongs to line 2, so I can use this equation. So now I'm looking for, this is T2 actually. Okay, now the question is, can I find a pair of T1 and T2 such that this is equal to that? So let's solve this equation. If you do the math, just if you simplify it, you will get something like T2 plus 1 plus T1, 2T2 minus T1, and minus T2 minus 2T1 is equal to negative 1, negative 1, 2. Should I explain how I got it? I'm sorry. Okay. Should I explain how I got it? Clear, right? So here you have T1 times something, and then the right side you have T2 something. Right? So move the term, that term T2 times to the left side, and then you have, okay, so I'm just going to write it here. So T1 times negative 1, 1, 2 minus T2, 1, 2, negative 1 is equal to 1, 1, 0 minus 0, 0, 2. Right? So that term from the right side goes to the left, so I have to change its sign. And then there is one term from the left side goes to the right, so I have to change its sign. Right? And then T1, so these guys here, they are actually minus T1 minus T2, T1 minus 2T2, 2T1 plus T2 is equal to 1 minus 0 is 1, 1 minus 0 is 1, 0 minus 2 is negative 2. Right? Oh, sorry. Okay. So now I have 3 equations and 2 variables, T1 and T2. And you solve it, you will realize that T1 and T2 actually do not exist. So if you, if you pick, so here I have 3 equations, right? Equation 1, 2, and 3. If you pick the first 2, equation 1 and equation 2, it's going to give you some value for T1 and T2. Then you pick 2 and 3, it's going to give you some different values. Because they are different, then such T1 and T2 do not exist. Right? Again, I started with this assumption that I can find unique values for T1 and T2 such that this relation, this equation here holds, right? Again, assumption was that such T1 and T2 exist and they are actually unique. So I went through with this assumption, I just simplified the equations, and finally I ended up with 3 equations for T1 and T2. If you pick the first 2, you're going to have some values for T1 and T2. I haven't solved it. I don't have the solution here. But let's say the value that they give you is just 1 and 2. When you solve this equation for the second and third one, it's going to give you different values, like 4 and 5. Then you're done. Your assumption was wrong. So that such T1 and T2, they just don't exist. Right? So we show that they are not parallel and they don't intersect, then they are skewed. Clear? Can I explain? Question? Okay. So again, when you go home, reread these examples. Please redo them. Just put a piece of paper on the solution and then think about the questions. Too much to learn. Clear? 1-5. Okay. Find the parametric equation in R2 means a two-dimensional space for a circle or for the following circle. X squared plus y squared is 9. It is a circle, of course it is. I'm pretty sure you learned it in calculus 1. Okay. What I'm going to be doing, it's not a proof. It's nothing. It's just the steps that one might use to come up with the solution, because the solution is already there, right? It just says that x is 3 times cosine t, sine and cosine functions, and y is 3 times sine t. You write this, you're done. In your exams, if you say that x is 3 times cosine t and then y is 3 times sine t, as far as I'm concerned, you're done. However, if you want to get familiar with the process to get there, it's as follows. What's the range, or what's the range of the values that x squared takes on? X squared is a positive number, as is y squared, right? And then based on this equation, x squared plus y squared is 9, right? So x squared can take on any value between 0 and, it's a question for you, and? No, x squared. 9. So that means that x can take any value between, give me the upper side. So x is always smaller than what? 3. And larger than what? Negative 3. So next step, let's divide the whole things by 3. So what's the range? What's the value range for x by 3? X divided by 3 is smaller than 1 and larger than negative 1. Okay, so that's it. If you know, I'm pretty sure everybody here is familiar with the two nice functions, sine and cosine. They are always between negative 1 and 1. Then here's your function. You can just say that x divided by 3, I'm just going to say that x divided by 3 is some cosine function. Why didn't I pick sine? It's okay. In your exam, if you want to say x divided by 3 is sine, it's still okay. But it's just pretty standard. For x, usually everybody picks cosine, and then for y, picks sine. I don't know why. So x divided by 3 can be represented by a cosine t, because it's still between -1 and 1, right? So let's go ahead with this thing. So x is 3 times cosine t. We are done with x. How about y? So let's say x is 3 times cosine. And then x squared, actually y squared is 9 minus x squared, which is 9 minus x squared is 3, 9 times cosine squared, right? And again can be simplified as 9 times 1 minus cosine t, which is 9 times sine squared, right? So y squared is 9 times sine squared. That means, not necessarily, right? But y can be expressed as 3 times sine. Then you're done, right? So x is 3 times cosine t, y is 3 times sine t. Again, it's not a proof, right? I didn't prove anything. I just gave you the steps, the process to get there. So in your exam, if you say that x is 3 times cosine and then y is 3 times sine, the only thing that you need to show is that your parameterization can be used in this equation. The only thing that you need to write in your exam is just this part, that 3 cosine t squared plus 3 times sine t squared is 9, which is really easy to show, right? This is the only thing that you need to show. it suffices to just write down that your parametric equation just holds. It just follows the same equation, just satisfies the same equation. That's it. No, not for today. I mean, just that's it for. Okay, guys. Example 1.7. It's quite a painful example. Let's do 1.6 today, and then we'll have enough time for 1.7. Hope you didn't mind. Okay. 1.6, sketch the curve in R3, which means three-dimensional space, with parametric equation x is cosine, y is sine, z is t. Right? Okay. Using that x and y part is actually, they give me the projection of this curve onto x and y plane. So that means so the whole thing, x and y and z, x cosine, y sine, zt is just a curve, right? If I look at this curve from the top, and when the z axis just goes through my brain, what I would see is just a circle, right? Why? Because this x and y, they have exactly same representation as that example 1.5. So 1.5, we said that a circle has this parametric equation, which is x is 3 times cosine, y is 3 times sine, right? Again, example 1.6, I have the same thing, except for that 3. So I still have cosine, I still have sine. So this curve, whatever it is, if I look at it like this, I'm going to see a circle, right? So this part is fine. Then there is another part, which is that z. That means that this curve has actually some sort of elevation. So, okay. So this is that curve when I look at it like this. However, there is a z involved. So let's start with t. So that parameter t, let's say t is 0. When t is 0, it just gives me the coordinates of this point. Cosine 0 is 1, sine 0 is 0, and z is t, which is 0, right? If I increase t, I'm just walking on this circle. However, there is this z. So let's say t is just 1, right? So I have cosine 1, sine 1, and then there is this z, and this z is 1. Do you get it? So it is a circle, however, it's like a spring which is kind of opened. When I look at it like this, still I see a circle. But when I look at it like this, so I'm just walking on this circle, but I'm just going up, right? So it's just like a spring. So this is the curve. Okay. You guys are tired, you have another class. You do it on Friday. So that was the thing.